Do you have annoying functional programmer friends who love to tell you that you're stuck in the 80s? OO is a failed experiment, and Gang of Four was all about making boomer programmers rich using techniques they would never actually use themselves. Or maybe you are that annoying functional programmer friend, pulling into programmer parties with your Arch Linux laptop, retro Ducati scrambler, and a ton of fresh perspective that could truly change the lives of your OO programmer friends. I've been both of these people over the years, the knuckle-dragging OO numpty and the pour-over functional It's too bad that functional programming has become such a charged topic, so let's put these stereotypes to rest and dig into the essential concepts, shall we? This is a video that I put together a few years back for the Imposter's Handbook video series, one of the many video courses you can see on my blog and also on my publishing site, bigmachine.io. I explain core functional concepts like immutability, currying, purity, and yes, monads. Hope you enjoy. First word that comes to mind whenever you hear functional programming is usually immutable. As I'm sure you know, it means not changeable in plain English. But how does that translate to programming? Moreover, who cares? If you're an object-oriented or OO programmer, you're used to creating classes and then instantiating them. You set their properties and send them messages which change their properties or tell you something about themselves. This is not possible with functional programming. There are no objects, no classes, no state, as you might think of with OO. There are only functions which transform things. You give a function what it needs. It hands you back what you want, hopefully. This might sound incredibly confining, but there are practices that go along with this idea that make it rather compelling. Let's take a look. If you want to follow along, you should have Elixir installed, version 1.3 or so, as well as Node, version 6+. Consider this assignment. Here I'm just assigning the variable friend to the map in Elixir, name Clara. Then I can take a look at this using standard out, using io.inspect. And there we see name Clara. This is a map in Elixir, and it looks a lot like an object in JavaScript or a hash in Ruby. The difference is you can't do something like this, which is setting the variable friend, and if I try and set friend.name equal to Mike, boom. Now that error message is a bit odd as it has to do with the way Elixir tries to match values using pattern matching, but essentially it means you can't change Clara's name to Mike. So what do? We ask the map library to update our map. This is going to look a little bit weird, but once I explain it more, hopefully you'll understand. So I'll set my variable friend, as I did before, to our map, but then I'm going to reset it here to map.put, which is going to update the key at that location, name, and set it to Mike. And then I'll look at it again, io.inspect friend. As we can see, our friend's name is now Mike. I don't blame you if you're completely underwhelmed at this point, and more than a little confused. There's just no graceful way to go about this, so I'm just going to throw you right in the deep end from the get-go. Here's what just happened. We created a map with a name key set to Clara. We asked the map library to put the value Mike in Clara's place. The map library gave us back a completely new map. Sort of. We'll get to that in a second. The friend variable was rebound to the new map. Elixir provides some helpful features which you don't find in more strict functional languages. For instance, in Erlang, functional language that Elixir is based on, you can't do what we just did, which is rebinding the friend variable. You would need to create a whole new variable, something like renamed friend, to hold the result of map.put. Elixir is a little less strict, so it looks like we're changing the friend variable. Well, that's the technical teardown. Let's discuss something a little bit more intangible. This code is just ugly. I would agree with you there, too. Fortunately, what I wrote is not idiomatic. I said at the beginning that functional programming is all about transforming data through a set of functions. Let's rewrite our code to support that idea. Much better. That toothy thing is the pipe operator and works in much the same way as its Unix counterpart. The result of a given function is piped into a following one as its first argument, and so on. Before we end our introduction to immutability, I want to underscore the notion of rebinding. Let's change our code around a little bit, and I'll reintroduce our friend variable here. This time, instead of setting friend equal to map.put, I'm going to pipe friend into map.put, and then I'm going to pipe that into io.inspect. On the final line, I'm going to io.inspect our original friend variable. Running this, and you'll see that our friend variable wasn't changed at all. Map.put simply passed back a new map with the updated key, which we piped into io.inspect. Thus, we have two different outputs. I don't want to leave you with the impression that data in a functional language like Elixir is just tossed around without any formalized rules or structure.
There are no classes in Elixir, but there are close relatives, structs, which do provide some of their utility. Let's formalize our code, making our intentions a little bit clearer and giving our friend some structure. Here I'll just create a module called friend, and inside I will say this is a struct by using the def struct keyword. And then I'll default the name to Clara. Next, I'll create a module called immutability, and in here I'm going to formalize the change name function, which is just going to wrap map.put. Next, I'll have a getFriend method that is going to instantiate our struct. This is idiomatic Elixir. At the very end here, let's take a look at what getFriend gives us. Looks a little bit better, don't you think? Structs allow you to set defaults for your data and give it a prescribed structure. Elixir also gives you some shorthand for updating a struct. Instead of using map.put, I can simply use friend and then the normal pipe operator, if you will, and then I can rebind the name to Mike. Running this, and once again, we get the same result as we did with map.put above, as the rebinding returns an immutable new friend struct. However, our original friend variable has not changed. If you're new to functional programming ideas, then none of this is probably convincing. It takes a while to get into the functional groove, so let's write some more code. 3 things that I want to focus on in this section are: 1, we are transforming data by passing it through a set of functions, which I kind of mentioned before. 2, we like small functions. 3, we can treat functions the same as values. That latter idea comes straight from lambda calculus. In fact, all of this does. That's where functional programming has its roots, in case that wasn't obvious. In addition, things work better overall if we focus on smaller, clearer functions. To see this in action, let's do some math. Here I'll create a module I'll call ops. And in here I'll create 4 methods: square it, double it, root it, and print it. This is idiomatic Elixir. Often you see functions that are just one line and very easy to read. To see this in action, let's take the number 4, and then I'll use the pipe operator and pass that directly into square it. And then I'll use the pipe operator again, pass that to double it, root it, finally print it. This is fairly typical Elixir in the functional world. Small, concisely named functions arranged as we need. We can simply pass some data along all the way through this transformation. This type of approach can work with anything. You just have to change your thinking a little bit. Let's compare and contrast a functional style versus an OO style, and I'll do that by creating a shopping cart in Elixir and then also in JavaScript. We'll start with JavaScript. And here I'll just create a class, an ES6 class. I have a constructor that sets an items property to an empty array. Then I have a method called addItem, takes in an item. Let's say we do some validations and checks and so on, and then I do this.items.push item. This is a fairly standard approach to building a cart, although yes, it's a little simple. Elixir is a little bit different. If we try and do the same thing with Elixir that we did with JavaScript, it just won't work. Functional languages don't have the notion of state, so holding on to an items array would just cause an error. We need to pass everything to the cart that it needs to operate, including the items. Here, my module cart has an addItem method. It takes in the items, and then it just adds the item to the items that you give to it. Let's tweak it a little bit more to look like functional programming. Much cleaner. It's still a little bit wonky, however. We're passing around arrays and maps without knowing what's going on. Let's clean this up just a little bit. When you're forced to do without state and objects, you begin to think in terms of data and things that happen to the data. In our example, we're using OO thinking by trying to represent a cart as an object which has behaviors and properties. And that's not very functional of us. Instead, we should think about things in terms of data moving through a process. The cart is our data, and our process is more accurately described as shopping. Here I've created a struct called cart, and then I have a separate module called shopping. The addItem function takes in a cart, as you can see, and I'm using pattern matching here to make sure that it is a cart struct. In addition, I'm taking in a map, which represents the item, but I'm using pattern matching once again to make sure there's a SKU and a price. If I try and pass anything other than something that matches this pattern, Elixir will throw an error. Then I just rebind the cart items to cart items plus the new item, and I reset the total on the cart and the count as well. I have a getCart and a saveCart method as well in my shopping module that will pull from the database and save to the database as needed. Finally, to wire it all together, I simply pull the cart out of the database using shopping.getCart. I pipe that result right into add item, and then I pipe that result into save cart. Finally, I inspect the entire thing. Now, I just threw a whole bunch of Elixir at you, and I hope you don't mind. But of particular note is how I'm able to use pattern matching to guarantee the data that this function needs is in the form that it needs it in. It's clear what this process is doing by reading the code, and the only change of state is in our database, which is acceptable in functional programming realms, but barely. There are two terms that you hear often in discussions about functional programming, in addition to immutability: purity and side effects. Both of these terms stem from the idea of immutability. The whole notion of interacting with a system outside the scope of the function you're in is called a side effect, something that happens as a result of your function being invoked. Working with a database, for instance, is referred to as a necessary side effect, because you're changing the state of something outside the scope of your function. The more you do this, the less pure your code is. Now, purity is not a term dedicated to functional programming. It refers to the level of interaction any code has with the outside world. You can write pure code in OO programming just as you can with functional. It just happens to have a little more focus in the functional world. Functional programmers like purity. It's easier to test a function that doesn't change behavior based on some external setting or function call. It's also easier to debug. The downside, if you want to call it that, is that you end up with more functions that are typically a lot smaller than what you might write in OO land. Now, there's a way to work with these small functions, however, as we're about to see. Functions, 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 they're everywhere. Organizing a program full of these small little functions can feel overwhelming, especially when you're just starting out with functional programming. Let's take a look at one of the very first practices that you're going to want to take advantage of: currying. Currying is the act of using smaller, single-arity functions in a chain rather than a large function with multiple complex arguments. It's easy to understand if we're using some code, so let's do that. Consider date night with your partner. Here, I just have a function, date night. I'm writing this in JavaScript, by the way. Takes in 3 arguments, who, what, and where, and I return a string. If we split this one function into a smaller set of chained single-arity functions, this is currying. Here, I'm just going to change this into a lambda. Night out equals who, which goes into what, which goes to where. This is a set of 3 functions chained together, and I return a final string. This looks a little bit weird, doesn't it? Especially if you're not used to lambdas. But how might we use this function? Take a look at this. I create a new variable, call it funtime, and then I'll invoke our nightout function. And then I'll invoke the next function and the next in line. 3 functions in a row. If I take a look at the output, you can see we have a final string. Does this look familiar to you? It should. It's function application. It's the exact thing we did when applying values to functions in lambda calculus, in the lambda calculus chapter of the book. Now, I know what you're thinking. Calling functions like this is goofy. Who would do this? I would agree with you. But this is where we need to understand the term partial application. What if I created a variable called dancing, and I set that to night out without invoking the following lambdas? I can just say night out dancing. I could reuse that if I create another variable called dancing with wife. And then I can invoke dancing and pass in wife. This invokes the second lambda. Now I can use my dancing with wife variable and just say club 9. If I take a look at our fun time, well, you can see we have the same output. This is partial application, where you get to reuse encapsulated functionality. This is the power of currying. Let's see something a little bit more concrete and applicable, however. I worked with a very nice, very opinionated developer recently who loves her object-oriented programming. I was trying to explain how I thought it would be fun to add some more functional ideas to the data access code we were writing. She was a little bit resistant. Actually, she was a lot resistant. Finally, she said, just show me what you mean. So I did. I started out with a curried function set for building a basic select query. Here I'm using the same chained lambda approach. I have a variable called select query, and then I have a set of curried functions: table, where and params, order, and limit. This is a chained set of lambdas. At this point, I simply need to evaluate what was sent in to each function call. If where was sent in, I'll create a where statement, same with order, same with limit. Then I can check the params length and then make sure it's an array. Finally, I'll return a JavaScript object representing our query, which has some SQL and the parameters that we require. I've written a lot of code for building SQL statements, and this is probably the smallest I've ever created, honestly. Using this is even more fun. I'll create a variable called users query, and then I'll set it to our select query, passing in users as the table name. If I want to take a look at this, however, I have to invoke that 3 times, which isn't a lot of fun, is it? Probably wouldn't want to create a query in this way, but this is where partial application comes in, and this is where we start having some fun. So we can start with our users query, then we can have users by email. We can set this to be a lambda that takes in an email argument, and then we can set this to be users query, email equals 1, which is the where statement, pass in the email argument, and then invoke that twice. If we want to take a look at users by email now, we can just use that directly. Boom, we have a built-up query. I think this is rather interesting and a nice way to reuse functionality. Let's round this out by plugging in PG Promise and actually querying some data to see if it works. I'll be using the Chinook test database for this. I'll change this up a little bit by passing in an exec callback. If exec is passed in, then I'll run the query that we just generated using PG Promise. Using this, if I wanted to take a look at all the rock albums, I can just build up, using partial application, an album query, and then an album search that builds on top of an album query, and then I can create something called, let's say, rock albums, where I do an album search for the term rock. If I want to use this, I just need to invoke it. I showed my friend this code, which I did. Her response was awesome. She sent me an email and she said, "Oh my God, that's equal measures ingenious and horrifying." Being able to reuse select query, album query, and so on, it almost seems like a twisted take on models at an arbitrary scope. Twisted indeed, but I like this approach. I think it's interesting. Let's have a very brief discussion about functors and monads. There's a great line from Douglas Crockford about monads, and he says, "In addition to it being useful, it's also cursed. And the curse of the monad is that once you get the epiphany, once you understand, well, that's what it is, you lose the ability to explain it to anybody." This is from his talk, Monads and Gonads, in December 2012 at the UE conference. I find this to be very true. That's why I want to keep this discussion as brief as possible and invite you to do your own investigation. But you should have a little bit of an itch in your brain right now, wondering, how am I supposed to orchestrate all of this functional stuff beyond simply currying my way to insanity? Well, this is where we get to abstract things a little bit, where structures like functors and monads, among others, come in. When you're slinging functions around as we have, you might want to have a higher level of abstraction for working with them, something to help you along the way, something that might wrap those functions and handle certain situations in a particular way. One thing that you might want to do is to interrogate or iterate over some values, such as an array or a struct, like a user. You could write a loop or do some kind of recursion if you wanted to, or you could orchestrate things using a set of functions. A popular way of doing this is to create a function which allows you to map values from a given object. Here I just have a class which I'll call monkey for now, and it has a constructor, it takes a value, and then it stores that value. And then I have a single function called map. Map takes in a function and returns an invocation on the current value. That's it. It's pretty simple, isn't it? This simple construct has a pretty lofty name. It's called a functor. Its only purpose in life is to run map over things that are mappable, and then give you back a new result. Functors have big brothers that will implement some logic on top of that mapping, namely returning some alternate values based on the data contained in your mappable object. For instance, you might want to access a name field on your user object, but you don't want bad things to happen if there is no name field. In other words, you don't want to get undefined back, or worse, you don't want to have an error. This is where monads come in, and where I start gracefully backing my way to the door. They're easy to understand in concept, and when you first encounter them, they can be a little anticlimactic. I don't know why this is. Monads really aren't terribly scary, but it's like some beautiful gateway to programming hell. You feel like you understand it, and then you start to use it, and then you get really confused and try and explain it to somebody else, and everything just blows up. I found Crockford's rule to be spot on, so I'm only going to discuss them a little bit and invite you to go and look at some examples that I have provided links for in the downloads. Let's create the simplest one, called the maybe monad. It's not really so scary, is it? See what I mean? It's tempting. We just have a class that we call maybe, has a constructor that takes in a value, and I'm setting an internal value. Then we have some methods, isNothing, map, and val. IsNothing just checks the current value to see if it's undefined or null. There's more checks I can have in here, but let's for right now just go with undefined or null. Then we have map. If our current value is nothing, then we're just going to return another maybe. And that's just going to be maybe of null. Otherwise, we're going to return another maybe, but it's going to be the result of the function invocation of whatever we passed in our map of the current value. Finally, we're going to ask for the value from this. If our current value is nothing, we're going to return an empty string. If there is a value, we'll return it. And that's it. This class exists to do one thing, which is to handle conditional values in an orchestrated, functional way. When you call map, you say, here's a function. Use it if there's a value. The trick, however, is that if there is a value for your monad, then map hands you back another maybe monad with its current value set as the result of your mapped function call. This means that we can move data through a chained set of functions without worrying about null or undefined values. We can now use our maybe monad to evaluate our where clause. If where has a value, then our lambda will be called. We'll get back another maybe with its current value set to our where clause. We can then call val and get our value back. If where isn't set, we'll get back an empty string, which is exactly what we want. So we can apply this to all of our arguments, our order clause and our limit clause. We could at this point build our SQL statement as we did before using a template literal, but where's the fun in that? Let's use our maybe monad one more time. And here I'm going to chain together maybe, and then we'll start with a select statement, and then we're going to map on our where clause and our order clause and our limit clause. So let's step through this. We start out with an initial value that we want to work with, and in this case, it'll be our select star from table statement. We move this value through a successive chain of functions, where it's applied to a function that is passed in via map. That value is then passed on to the next in the chain. Now, if you're thinking that this looks a lot like Elixir's pipe operator, you'd be correct. Here's the final code for our query. If you're interested in reading more about monads, I found a wonderful blog post from James Sinclair, which is not only well written, it's gorgeous. Look at this thing. I was able to stay with the explanation up until about the last third of the article. I've tried to reread it about 12 times now, but the first 2/3 are really good and they sink in. The last one, I don't know, I just had a hard time with it. I couldn't quite get it. Well, if nothing else, hopefully you understand monads at a very, very high level. If not, please don't give up. I encourage you to follow the links above, have a look at some more code, see if your brain changes shape a little bit, as mine has done.